Okay, we're looking at the 2020 Level 1 Mechanics exam. First question, Felix Baumgartner is famous for jumping from a height of 40 kilometers above the Earth. Fell for over 6 minutes before opening his parachute. There's him jumping there. Below is a graph of his speed versus time for the first 60 seconds of his jump. So remember, when we're looking at a graph like this in the exam, we've first of all got to really make sure we've identified what type of graph it is. And this one is speed versus time. It's not distance versus time. So this axis here is showing his speed going from low to high speed. And this, of course, is time. So here's our speed time graph. And we can see that at time 0, he started at a speed of 0 meters per second, and then over the course of the first 30-something seconds, he's speeding up. It's going faster and faster in that time. So that means he's accelerating there. So let's have a look. 1. Describe Felix's motion in section A and C of the graph. So section A, this first section here, section A, we can see he's gone from 0 up to 350 meters per second, and his speed is increasing at a regular rate. So we could say at this section A, we could say there is constant acceleration. It's speeding up. And section C, that's the section here, we can see that the speed is constant at 350 meters per second. So we'll say constant speed in section C. And state the maximum speed reached by Felix. We can see again that the speed increases up into this maximum here of 350 meters per second. Use the graph to calculate Felix's acceleration for the first 30 seconds. So acceleration, let's have a look. These are the formula that we were given with this paper, and we can see acceleration is the change in velocity, the change in speed, divided by the change in time, the time it took. So let's have a look then. We can see for the first 30 seconds, starting at 0, going through to 30 seconds, we write our formula. A is equal to change in speed divided by change in time. The change in speed from 0 to 30, it goes from 0 meters per second up to 300. His velocity after 30 seconds is 300 meters per second. So our speed is 300 meters per second divided by the time of 30 seconds. So that gives us an acceleration of 10 meters per second squared. And the units are there for us. Now, use the graph to calculate how far Felix fell in the first 30 seconds. So remember, for a speed time graph, the area under the line, equals the distance traveled. So we need to find the distance underneath the graph for the first 30 seconds. So here is our line here, up to 30 seconds. We need to find this area here that I've highlighted in green. And remember, the way we calculate our area is the area is equal to, of this triangle, is the half times the base times the height. So it's a half. The base length is 30 and the height is 300. So there's our equation there, a half, which is equal to 4,500 meters. And don't forget, we've got to include our units for that as well. Part E is our graph again from the previous page. Draw and label arrows in the diagram below to show the size and direction of the vertical forces acting on Felix in section A and section C of the graph. So section A, we can see that the velocity increases from 0 up to 300, so we can say he is accelerating as it was in the first question. So for acceleration, we need to have a net force. So in section A, there needs to be a net force. That means the force downwards has got to be larger than the force upwards. So let's identify them. His force down, of course, is his weight force, which we might call Fw. His weight force, and remember that will equal mass times gravity. And falling down, what's the force pushing him up? It's the friction force. Friction force we'll call Ff. We might call it a drag force, but we'll stick with friction at the moment. And because the Felix is accelerating, his friction force, his weight force is larger than his friction force. So that gives a net force downwards, producing an acceleration. And now next, our second part here in part C, we've got Felix again, and his weight is the same as it was before, his weight force, always equal to his mass times g. But now we can see in section C he's going at constant speed, and remember, for constant speed, he's not accelerating, therefore the resultant force is equal to 0. The resultant force must equal 0. That means the force up and the force down are the same. So we've got a weight force down of mg, so the friction force must be equal and opposite pushing up. That's his drag force, the wind resistance pushing him up. And note when we draw this that we've got to be sure that our weight forces are the same in both cases, that the friction force when he's not accelerating is the same size but opposite direction to his weight force, and when he's accelerating downwards his friction force is smaller than the weight force downwards. So part 2, explain the motion in section A and C by comparing the vertical forces acting on Felix. So let's have a look in section A. We can say the weight force is greater than the friction force, therefore there is a net force downwards. And we can say that unbalanced forces, net forces, unbalanced forces, produce acceleration. And our next section here, in section C, let's describe the motion. We can say the weight force is now equal to the friction force, therefore the net force is equal to 0. Net force is 0, therefore acceleration is 0. Question 2. I was excited about this one. Each year firefighters run up the Sky Tower. Lindley is preparing for this event by running up the stairs in her building, and each day she climbs to a height of 25 meters, and below is data from 2 of these days. So here we've got the mass of Lindley and her equipment in kilograms. Both days is the same mass, and the height she runs up, again 25 meters, and the time taken to climb 25 meters on the first day is 50 seconds, on the second day is 30 seconds. That's quite a decrease in time, so she's really cracking it the second time. Compare the work done and power produced by Linley on each of these 2 days. So for that, we'll have a look at our equations, and we see work done is force times distance, and power is equal to work divided by time. So there's the 2 equations we're going to use at the moment. So calculate the work done on each day. So let's have a look at day 1. Work done is equal to force times distance. Now she has run up all of these stairs, and we know she's got a mass of 80 kilograms altogether, and we know the distance is 25 meters. 25 meters. So let's have a look then. Work done is equal to force times distance. Now, we've only got her mass. We don't know the actual weight force she's overcoming to run up those stairs, but we remember our weight force is equal to mass times G. So her weight force is 80 kilograms, and G, we are given that G is 10 newtons per kilogram. So we can say her weight force is 80 times 10, so her weight force is 800 newtons. So this is the force she has got to apply to go up to overcome her weight force. She's got to apply a force of 800 newtons to lift herself up the stairs. So our work done is equal to the weight force times the distance, which is equal to weight, remember, mg times d is equal to 10 times 80 times 10 is 800 times 25 meters. So her work done each day is going to be 20,000. And because it's work done is energy, so our unit is going to be joules. Remember, units for energy is joules. So that's the work done. That's how much energy she must provide to lift herself up then, and power is equal to the work divided by the time. So that's going to be 20,000, and in day 1 her time is 50 seconds divided by 50, so her power initially is going to be 400. Now, what is the unit of power? Nice joke. 400 watt. What is the unit of power? Okay, so that's day 1, 20,000 joules, 400 watts. On day 2, work done is equal to force times distance. Her weight force is the same, the distance is the same, so the work done is going to be the same, 20,000, and again it's energy, it's in joule, and power is the work divided by the time. The work is the same, 20,000 joules, but now we can see she's done it in 30 seconds, so the power is going to be 20,000 divided by 30 equals 667 watt. So we can see that she is exerting more power on day 2 than she was on day 1. And just to refer back for 1 second that we're asked to compare the work done and power. So we'll actually need to be writing something about this. So we might say the work done is the same on both days, but the power the power is greater on day 2 because the time is less, because she runs up in a shorter time. She's quicker, time is less. Okay. And while she's running up, she looks down the stairwell and her helmet falls off. Remember, she's in full firefighter gear. The helmet falls between the stairs without touching them and falls down to the bottom. She estimates the helmet would hit the ground at 20 meters per second. Using conservation of energy and assuming no other external factors, calculate the height from which the helmet fell. And the mass of the helmet is 1.5 kilograms. In your answer, you should calculate the kinetic energy of the helmet just before it hits the ground. Describe from which form this kinetic energy has transformed. So, calculate the height from which the helmet fell. So she has gone up 25 meters. So that means there's been an increase in potential energy. Potential energy has increased. And we'll want to check the equation for that. So the helmet has got an increase in potential energy as it's gone up. And then as it fell off, that potential energy is converted to kinetic energy as it falls down. Kinetic energy as it falls down. And let's again have a look at our formulae for this. We've got gravitation potential energy equals mass times g times the height. And over here we've got kinetic energy is equal to half mass times velocity squared. So let's go back to where we were. Use the conservation of energy and assuming no other external factors, calculate the height from which the helmet fell. So we can say that conservation of energy, we can say that the gravitation potential energy, and I'll write EP grav, is equal to the kinetic energy of the helmet as it fell. Now gravitation potential energy is mg delta h, the height, is equal to half mv squared. So we've described from which form this kinetic energy is transformed. We've said it has come from gravitation potential energy, and we need to calculate the kinetic energy of the helmet just before it hits the ground. So working on this equation here, it's first of all we can calculate the height. When we look at this equation, we can see we've got mass on both sides, so we can divide both sides by m, and that cancels out, and we get g times delta h is equal to half v squared. And we're given g is 10, and the height we don't know is equal to half, and the velocity is 20, and it's squared. Don't forget that squared. Don't forget the squared. It's a shame to lose some marks because we forgot to square it. And then we can say 10 times delta h is equal to a half times 20 times 20. And I like to do this. Let's divide both sides by 10. And that will give us the height is equal to 20 meters. Okay, so we've calculated the height from which the helmet fell, and we need to calculate the kinetic energy of the helmet just before it hits the ground. So kinetic energy, according to our formula, is equal to 1/2 mv squared. The mass of the helmet we're given is 1.5 times velocity squared again is 20 meters per second squared, which means the kinetic energy is equals 300, and remember it's energy, so it's going to be in joules. So explain why the helmet will not reach a speed of 20 meters per second. So remember it said before that considering no other factors, but the simple fact is there is air resistance. There is air resistance, and that means that there will be a force of friction upwards, and because there is friction, therefore some of the energy from the gravitational potential energy some of the gravitational potential energy will be converted to, what do we get when we have friction? Some of it will be converted to heat. Therefore, not all the gravitational potential energy will be converted to kinetic energy. Therefore, it doesn't reach 20 meters per second. It'll be somewhat less. It won't be much less, but it will be a little bit less. Questions are in. Last question. NASA has revealed a possible vehicle to travel over the Martian surface. We've actually got that there. It's travelling over it at the moment. There's a couple of them there. Mars is a very dusty planet, with much lower gravity than ours. Gravity on Mars is 3.7 newtons per kilogram. On Earth, it's 10 newtons per kilogram. So that means the gravity is about a third, which means our weight will be about a third, really. And this creature is not a real one. Okay, define mass and weight. We can say mass is the amount of stuff, the amount of matter, the amount of material that something's made of. Whereas weight is the effect of gravity on the object. It is the force of gravity. The force of gravity, the force of attraction, between two bodies with mass. Explain what 10 newtons, or the symbol here, 10 newtons, kilogram to negative 1 per kilogram. Sometimes people used to write it newtons per kilogram, newtons per kilogram. And in this case, it is 10 newtons per kilogram. That means for every kilogram mass, there is a force of gravity of 10 newtons. So an 80 kilogram mass will experience a force of 10 newtons per kilogram, so that will be a force of 800 newtons. I've lost the ability to write. Okay, part C, I hope you're enjoying this as much as I am. Calculate the weight force of the Mars vehicle when it's on Earth and when it's on Mars. The mass of the vehicle is 2,500 kilograms. So, part 1, the weight of the vehicle on Earth, where G is that. Here is our equation, weight force, we'll put weight force on Earth is equal to mg. The mass is 2,500 kilograms times G on Earth is 10 newtons per kilogram. So the weight force on Earth is equal to 25,000. And remember, it's a force, so our units for force are newtons. And the weight of the vehicle on Mars, remember again, the weight force, formula for weight force is equal to mg. The mass is the same. Remember, mass is the amount of stuff, the amount of matter, the amount of material. So that's the same whether it's on Mars or Earth. So 2,500 times G, the strength of the gravitation field, times 3.7. So that's equal to 9,250. And again, it's a weight force, so the answer is going to be in Newton. Okay, there are 6 wheels on this vehicle, as you can see over there, 6 wheels with a surface area of 0.25 square meters per wheel. So if there's 6 wheels, we're going to have more surface area. So calculate the total pressure that this vehicle would exert on Earth. And here are our formulae which we've been given, and we can see pressure is equal to force divided by area. So calculate the total pressure that this vehicle would exert on Earth. Remember, there's 6 wheels. This is the area. So here is our formula. Pressure is equal to the weight force. Actually, let me write weight force FW divided by area. So the weight force on Earth is 25,000 divided by the area of the wheels pressing down on the ground. Each one is 0.25 and there's 6 of them, so we've got to have an area of 6 times 0.25. That gives the total area. So that gives the pressure on Earth equal to 16,667. And now we've got to have our units. Our units are force divided by area, so we could have newtons per square meter, which is equal to pascals. There we go. Okay, the Mars vehicle is based on similar soils on Earth and Mars. Explain why the Mars vehicles sink to different depths on each planet. You should support your answer with calculations. Okay, we've got the pressure that the Mars rover exerts on Earth is 16,667 newtons per square meter or Pascal. Let's have a look at the pressure that it exerts on Mars. And again, pressure is equal to the weight force divided by the area, and our weight force on Mars was 9,250 newtons divided by the area. Again, the area is 6 lots of 0.25 meters. So the pressure on Mars is equal to 6,166 newtons per square meter, or this many pascals. So we have a pressure of this much on Earth, but only this much on Mars. So we could say the rover exerts a greater pressure because of the stronger gravity, a greater pressure on soil on Earth. Therefore, it will sink deeper on Earth. And from our equation, pressure is equal to F divided by A, that's our weight force divided by area. We can say that if Fw is smaller, then pressure will be less, and the opposite as well. So that's it. I hope you found that pretty straightforward. You'll have an hour to do that in the exam. Best wishes with that.